Hey guys, so in the last lecture we were discussing various boiler efficiency measurement methods in which we saw two methods, that is one is direct method and another is indirect method. So we discussed all the equations for indirect method, and now we'll list out all the equations of indirect method again on one table. So in this slide I have listed out all the equations of indirect method, uh, that is losses due to hydrogen, moisture in fuel, in air, in complete combustion and everything. So all these equations we will use in the example, in the coming example. So we need to remember all these equations. So now let's see one example. So suppose this question is given. So in this question, uh, the question is that find the boiler efficiency by indirect method. So by indirect method we have to find the boiler efficiency. So in this, carbon content is given in percentage, hydrogen content is given, moisture content is given in fuel, the gross calorific value of fuel is given, then surface temperature of the boiler is given, then humidity, and all the parameters are given. So we need to find one by one all the losses. So the first one was heat loss due to dry flue gases, L1. So the formula for L1 is mcp mcp into Tf minus Ta divided by GCV, or CV of the fuel. So here, first of all, CV of the fuel is given, which we are going to use again and again, that is 10,000. So CV of the fuel is given. Then next, MCP. So what is M? So M is mass of dry flue gases, so that is given 21.36 mass of dry flue gases. Then CP. So what is CP? CP is specific heat. So specific heat of flue gases is given 0.23. 0.23 is given. Then TF minus TA. So TF is flue gas temperature, that is 190, minus TA. TA is ambient temperature, that is 30 degrees Celsius. So all the values are given. So you will get L1 answer is 7.86 percentage. 7.86 percentage. Similarly, the next we will find L2. Okay, so similarly we will find L2. So L2 is heat loss due to evaporation of water due to H2 in the fuel. So due to hydrogen content. So for hydrogen content the formula is 9H2 into 584 plus CpTF minus Ta upon CV of the fuel. So TF minus Ta and CV are given. So only new term which is added is H2, that is 12%. So we have to take is at 0.12. Similarly, we will find heat loss due to moisture of the fuel. Moisture in the fuel. So moisture in the fuel is given 0.5%. So we will use same formula. Then next is heat loss due to moisture in the air. So how much moisture is in the air? So that is, so for moisture in the air, uh, mass, that is of flue gas, is 21.36 into humidity, that is 0.025, is multiplied, and into Cp minus Tf minus Ta. Then similarly L5, that is losses due to incomplete combustion, that L5 is directly given in the question. Then L6, losses due to radiation and convection, that is also directly given, it is 0.38. So we will add all these losses and subtract from 100, so we'll get efficiency as 84.26 percentage. So in such a way we will find all the losses. So L1 we got 7.86%, L2 7.08%, L3 0.033%, L4 0.38%, and L5 and L6 are given already. So this is an example which was asked in GTU. So similar examples can be asked in exam. So next topic is reasons for boiler tube failure. That why the tube of boiler uh, gets filled. So below are the following reasons. First is poor quality water. That with increasing operating pressures, if pressure is too much high, then feed water quality becomes even more critical. So if pressure is high, then water quality becomes more important. So it is a reason, if it's an impure water, then your tube may fail because it can increase more pressure due to impurities. Then coal quality. So using different type of coal for emission or economic reasons has adversely affected the capability, operability and reliability of boiler and boiler auxiliaries. So we need to use high calorific value coal, such as lignite, or so we should not depend on peat coal. So high calorific value good quality coal can be used, so that our boiler is not very much affected and we can get more reliability. Then next is cycling operation. So many a times that the base load designed for the boiler have been placed into cycling duty, that we have decided the base load, that what load it will operate, which has a major impact on boiler reliability, as indicated by occurrences of corrosion fatigue serious corrosion fatigue in water touched circuitries. So where water is touched in circuitries, then economizer inlet header, where the economizer is kept, then thick wall header damages and etc. So cycling operations are important. So the load for which the boiler is designed, so it should be placed in that cycling duty only, otherwise there will be major reliability issues, and this may be the failures, various fatigues. Then fourth point is NOx, that is nitrogen oxides emission. So deep staging combustion for NOx reduction has produced serious water wall fire corrosion for high sulfur coal firing, especially in supercritical units. So if this kind of emission takes place, so we require to reduce the nitrogen oxides emissions. So in order to reduce it, serious water wall fire corrosion is taking place, and high sulfur coal firing is taking place, so due to which the tube may get filled. Then last is aging. So a large percentage of existing fossil fired units are exceeding the design life, that for what life it was designed, it's supposed 20 years, 10 years, so that life has been exceeded, so that we need to take care of. So without plans for retirement, these vintage units are carrying major loads and power generation. So if we are not replacing this all pipes, then the tube may fail. So these are the major reasons for boiler tube failure. So again, once I will repeat, there is poor quality water, cold quality cycling operation, nitrogen oxides emissions, and aging. So these five are main important points for failure of the boiler tubes. Then next topic is energy conservation opportunities. So what are energy conservation opportunities in boiler? So how we can conserve energy in the boiler? So various opportunities we can get in the system, boiler system, related to this all parameters, that is heat transfer, combustion, etc. So we'll go one by one. So first is stack temperature. So stack temperature should be as low as possible. However, it should not be so low that water vapor in exhaust condenses on the stack walls. The stack temperature greater than 200 degrees Celsius indicates potential for recovery of waste heat, and this is important in fuel containing significant sulfur, as low temperature can lead to sulfur dew point correction. So stack temperature should be kept as low as possible. So this is an opportunity where you can conserve the energy. And second opportunity you can get is in feed water preheating using economizer. So the potential for energy savings depends on the type of boiler installed and type of fuel used. So typically flue gases leaving modern 3 pass shell boiler are at temperature 200 to 300 degrees Celsius. Thus there is a potential to recover heat from these gases. So the flue gases which exit the temperature from the boiler is usually maintained at 200 degrees Celsius. So the sulfur dioxide in flue gases does not condense and causes corrosion in the heat transfer surfaces. So modern 3 pass shell boiler firing natural gas with flue gas exit at 140 degrees Celsius, a condensing economizer would reduce the exit temperature to 65 degrees Celsius, increasing the thermal efficiency by 5%. So here the preheating of economizer is done. With the help of economizer is done preheating of feed water. So as told that two aspects are there. First is that we need to condense the sulfur content, and we need to transfer the heat to the incoming water. So that are these two condition. Then next is combustion air preheat. So air which is inducted in the boiler should be preheated in an alternative to feed water heating. So in order to improve the thermal efficiency by 1%, the combustion air temperature must be raised to 20 degrees Celsius. So whatever the air is, we need to raise by 20 degrees Celsius, not raised to, but by. Means if the entrance air temperature is 25 degrees Celsius, so we need to raise to 45. So 20 degrees Celsius raise is required. Then incomplete combustion. So incomplete combustion can rise from a shortage of air or surplus of fuel. That is, if there is shortage of air, means the combustion will take place incomplete combustion. And if it is excess air, then also the combustion can takes place incomplete due to poor distribution of fuel. So with coal firing, unburnt carbon can comprise a big loss. So if combustion has not taken place 100%, then unburnt carbon is comprising a very big loss. So it occurs as grit carryover, and carbon in ash may amount to more than 2% of the heat supplied to the boiler. So 2% of heat can be supplied to the boiler extra. So to obtain the complete combustion, the great stokers, large pumps will not burn out completely. So in stokers also small pieces of block, small pieces can block the air passage. So generally here the main reason for incomplete combustion is non-uniform fuel size. So we need to uniform size of fuel should be used for complete combustion. So size of fuel should be uniform. The next is radiation and convection heat losses. So the external surfaces of the shell boiler are hotter than surroundings. So the surfaces thus lose heat to the surroundings depending on the surface area and the difference in temperature between the surface and surroundings. So the heat loss from the boiler shell is normally a fixed energy loss irrespective of boiler output. So the heat loss depends on the surface area and not on the how much output it is getting. So with modern boiler designs, this may represent only about 1.5 percentage on the gross calorific value at a full rating, but will increase to around 6% if boiler operates at only 25% output. So if the output is very less, then the losses will be very high if it is operating at 25% output. Then automatic blowdown control. So uncontrolled continuous blowdown is very wasteful. So automatic blowdown controls can be installed that sense and respond to boiler water conductivity and pH. So a 10% blowdown in 15 kg per centimeter square boiler results in 3% efficiency loss. So it results in 3% of efficiency loss. Then 7, reduction of scaling and soot losses. So in oil and coal fired boilers, soot buildup on tubes acts as an insulator. So we need to remove this soot and scaling, so which may increase the efficiency. So it is estimated that around 3 mm of soot can increase the fuel consumption by 2.5 percentage. Due to increase in fuel gas temperature, the periodic offline cleaning of radiant furnace surfaces, boiler tube, banks economizer, and air preheaters may be necessary to remove the stubborn deposit. So this 3 mm soot can increase the fuel consumption by 2.5%. Then next is reduction of boiler steam pressure. So this is an effective means of reducing fuel consumption if permissible by as much as 1 to 2 percentage. Lower steam pressure gives lower saturated steam, and without stack heat recovery, a similar reduction in the temperature of the flue gases temperature results. So this is one kind of efficient measurement efficiency. We can get efficiency. The next is effect on boiler scheduling. So since the optimum efficiency of the boilers occurs at 65 to 85 percentage of full load, it is usually more efficient on whole to operate a fewer number of boilers at higher loads than operate a large number at low loads. So if there are 3 to 4 boilers, and if the load is less and you are operating all the 4 boilers, then the efficiency will be less. And in case if you are operating only 2 to 3 boilers at full load, then the efficiency will be high. So that you need to schedule. Then boiler replacement. Last is boiler replacement. So old and inefficient, not capable of firing cheaper substitution fuel, over and undersized for present requirements, and not designed for ideal loading conditions. So if these are the reasons, then we need to have a boiler replacement. So we need to replace the boiler. So these are the main opportunities where we can conserve the energy. So all financial and engineering factors should be considered for boiler replacement, since boiler plants traditionally have a useful life of well over 25 years. Replacement must be carefully studied. It should be studied very carefully. So this was the energy conservation opportunities, and we have also discussed various factors for boiler tube failures, and we also seen one example. So next time we will see boiler startup and shutdown, and that is the last topic of this boiler conservation, energy conservation in boilers. So thank you very much.